Hello, everyone. My name is Kristen Privatera Johnson. I am a PhD student with Andre Punt here at the University of Washington. I am your substitute moderator for today's presentation. Miko was not able to attend, but it is my great pleasure to introduce today's workshop leader, Mark Maunder. So Mark is also an alum of the UW Fisheries program, working with folks like Ray Hilborn, and also cites folks like Andre Punt and Dave Fournier, and a long list of mentors that have helped guide him through his fisheries science career. And Mark has really done a little bit of everything, and it's always a pleasure to host him in the seminar series. If this is your first time attending the UW Think Tank workshop, I'll let you know that the history of this workshop is not too different from the inspiration of some of the CAPM work, or all of the CAPM work that Mark Maunder has been involved with, where the two NOAA centers close to the University of Washington, the Alaska Fisheries Science Center and the Northwest Fisheries Science Center, and UW realized, hey, we're all working on, oops, apologies for that. We're all working on similar stock assessment things, and we should have workshops to talk about our in-progress work so that we can do synergistic activities and keep up with our peers. And so Mark is here today to continue this tradition and follow up on, gosh, I want to say you even came to Think Tank during the pandemic lockdown to start advertising for this good practices workshop. Mark, does that sound familiar to you?
I did a presentation, yeah, I'm not sure when it was though.
Who knows? But now you're coming to us to talk about that workshop has happened, and you've got some new thoughts about the directions we're going, and it looks like for tuna specifically. And with that, Mark, would you like to have folks ask questions and contribute to discussion while you're presenting, or wait until you're finished?
Probably better at the end, I think.
No problem. So folks that are online, well, everyone's online, you can use the questions box of GoToWebinar to submit questions while Mark is talking, and they come to me as the moderator, and they won't produce any distracting notifications from Mark. So I'll hold on to those questions as you have them, and when Mark calls for them, we'll open up the discussion, and we'll even be able to unmute and have discussion later as time allows. With that, thank you for listening to my preamble, and help me welcome Mark virtually onto the stage. Mark, take it away.
Okay, thanks. Good morning, everyone, and thanks for having me at the UW Think Tank. Today I'm going to be presenting some of my ideas about stock assessment good practices, coming out a lot of the CAPM work, and particularly focusing on tuna, since that was the more recent workshop we had, and also is my area where I'm working. Simon Hoyle in New Zealand is a collaborator on this, but anything I say today that you don't believe in, just blame it on me, not on Simon. Okay, and for some reason my screen is not moving. Okay, there we go. So just to put some of the CAPM workshop series in context, it really started 20 years ago as the IATTC October Stock Assessment Workshop Series, where we had a workshop on recommended diagnostics for large statistical stock assessment models, which I coordinated in collaboration with Shelton Harley, who was also working at the IATTC at that time. And in that stock assessment series, we covered a lot of different topics about stock assessment, but the participation rate was pretty low. And so in 2012, Paul Crone, Bryce Simmons, and I got together to form CAPM, and the main idea here was to try and get a bit more funding in that to push the CAPM or the stock assessment workshops and try and get a better participation. And so since then, we've had quite a few workshops. We've covered all the different topics in that are components of fishery stock assessments. And we've also had two sort of summary workshops where we've brought in keynote speakers to talk on the different topics and sort of more of summarize all the work that's been presented at previous workshops. And one was last year in Rome, and then the second one was in New Zealand early this year, which focused more on tuna stock assessments. And as you can see there, we've had quite a few more participants compared to the IATTC ones, and particularly recently as we've moved to hybrid or virtual workshops, we've been able to get a lot more people in through the virtual system. And for each of these workshops, or for most of them, we've actually put together a special issue in the journal Fisheries Research. And that's a good way to sort of make permanent the research that everyone presents at the workshops. And currently we are in the process of putting together a special issue on good practices in fisheries research. And as you can see here, we've already got quite a good list of topics published, ranging from recruitment, growth, catch per unit effort standardization, data limited methods, data weighting, a general paper by Andre on good practices, and also a couple on spatial structure and spatial structured models. But we still have time if anyone has any manuscripts they want to submit. The submission deadline is the end of this year. So one of the big focuses of CAPM is basically this good practices program, which is mainly the workshops and the special issues, but we also had a postdoc, Juan Valero, early on in CAPM's history, and had visiting scientists, all working towards trying to create better methods for doing stock assessments. And one way of looking at this is looking at the process that goes into creating management advice from stock assessments. And you can think about the CAPM process is really trying to come up with some kind of expert system to create this advice. And so you start off with a conceptual model of the system and to give you a better idea of what processes are important, what data is available, and all the different components, and then turn those into stock assessment models. And the way you do that is through some kind of default assumptions, so that you have a good stock assessment model to start with. But it's not going to be the perfect model, so then you have to do some work to try and improve those models. And you might have multiple models because there might be uncertainty about the system or different hypotheses about the system. And so the diagnostics will have a look at those assessments, and if they fail the diagnostics, then you want to try and improve those models to be able to get a better model. And you can cycle through that process a few times, and if you aren't able to improve the models, then you would discard those and not use them. But if they were able to pass your diagnostics, then you would put them on to the ensemble, and that would be used for management advice. So the workshop series is really looking at coming to define what those default assumptions might be, because you want to start off with a good set of assumptions. But there's also some other parts of CAPM work that are in the system, and so Carolina Mintavera, who works at the Tuna Commission, has been doing a lot of work on how to develop these conceptual models, which is something that a lot of people haven't been doing before they create their stock assessments, including myself. And then Felipe and his group in Hawaii have been trying to develop diagnostics by doing a lot of simulation analysis and evaluating the diagnostics. We also had a specific CAPM workshop on model weighting, and that's working out how you should be combining the models on the ensemble to get your management advice. And so we've really been covering a lot of the aspects of the stock assessment process in the CAPM workshop series. And I think the main reason why the CAPM workshop series has been so successful is because there's been a lot of focus on discussion. And so after every presentation, there's a good amount of time for questions. And then after every subtopic, we have quite a long period for discussions. And so bringing in keynote speakers, having contributed presentations and lots of discussion periods has really helped the success of CAPM, as well as the special issues that memorialize a lot of the work that's been presented. So yeah, a lot of this is coming out of what I'm going to talk about today is coming out of the tuna stock assessment good practices workshop, but that built on all the previous workshops, and it was held in Wellington in March this year, and it was funded by ISSF, NIWA, and I think that's pretty much it. You can see here we got we covered the range of topics in stock assessment, and we had a good number of speakers from both the tuna and the non-tuna world. And the presentations from the workshop are recorded, and you can get them on the CAPM workshop CAPM website. So I'm going to talk about sort of my views on what tuna good practices are, and it's based on mainly on the final summary discussions that we had in the last day of the tuna workshop. Some of it is coming from what I can remember from the Rome workshop as well, but a lot of it is also based on my own experience and my own opinions. I was hoping, particularly for this talk, but for other things, is to integrate a lot more information from the presentations at the tuna good practices workshop, the Rome workshop, the special issues, and also a lot of the independent or external reviews of tuna assessments. But unfortunately, I got other duties, so I haven't had time to do that. But that will be something I might hopefully do in the future, particularly for the report for the tuna good practices workshop. So now I'm going to go through each of the topics that are involved in creating a stock assessment, and just discuss some of the ideas I think about the good practices for those topics. So the first component is to come up with the stock structure that you're going to use in your assessment, and this is fundamental. Without developing a good stock structure, you can actually have a misspecified model, and it could all be just because you're either modeling part of a stock or you're modeling two stocks that should be treated separately. So to do this, you want to come up with your conceptual model first, and this is an interdisciplinary approach because there's a lot of different aspects that go into creating the conceptual model and all the data that's available. But once you've done that, you really want to represent in your stock structure well-documented factors that create stock structure, such as spawning and feeding migrations. And then those can be used either to create spatial models or possibly separate independent models. And so if you have situations where you have really low interaction identified in the population, then you should be modeling isolated stocks. If there's high interaction, then you probably should be using the areas of fleet approach or something similar to model the spatial structure. If there's intermediate interaction, then that's when it gets really difficult to model. A lot of the time you might be relying on tagging data to either determine the stock structure or to model the interactions between subpopulations. But particularly for tunas, the tagging data is usually too problematic to use in an integrated model. And you end up getting a lot of control in the estimates of movement from length composition data, and that's really problematic, particularly for tunas. And so you have to be really you have to think really carefully before you use tagging data in these analyses. And when you're doing the fleets as areas as fleets approach, that's in the high interaction situation, then you want to use clustering methods on the length composition data to identify the potential fleets. The next component I'm going to talk about is CPUE analysis. And this is particularly important for tunas again because we don't have surveys, so we're relying a lot on the CPUE data for our indices of abundance. And when you do a CPUE standardization, it should be really conducted over the area that's considered the whole stock or each substock in a multi-area model. And you want to use a spatial temporal model to analyze the data and calculate the index by summing the product of the predicted CPUE and the size of the area for each spatial cell. And the composition data that you're going to use for that index should also be generated by a spatial temporal model, and you should be weighting the length comp in a particular cell by the CPUE index. But for the extraction fishery that's related to that index, it should have its own composition data, and this should be spatially weighted by the catch. And then the index and the fishery should have different selectivities. So the first biological process that I'm going to talk about for the stock assessments, which is recruitment, which has had a lot of history, and people probably know my thoughts on this, and I'm going to go into a little more detail on recruitment. But Liz Brooks also has produced a keynote manuscript for the special issue, and she has a similar thought as the first comment here, which is basically when you're estimating the stock assessment model, you should assume recruitment is independent of stock size, so steepness is 1. If you're going to have anything of a stock recruitment relationship, it should really be put into precautionary limit reference points rather than into the estimation. And also those any reference points shouldn't be rated to yield per recruit in cases where the fisheries select juveniles, which is often the case for tuna stock assessments. Autocorrelation is typically difficult to estimate, though it's always there in recruitment. But during the estimation period, you can probably ignore it and fix the standard deviation at a reasonable value if you're using the penalized likelihood approach like you need to do in a lot of the software packages we use, like stock synthesis. Use the bias correction ramp. One sort of caveat on that is that there does seem to be a trend that you should be fixing the standard deviation used in the recruitment penalty to a higher value than you would normally think, just to ensure that you're not constraining the estimates of recruitment. However, there hasn't been a lot of work done on this yet, and there might be possibilities where recent recruitments might be estimated inappropriately, or if you're doing the management quantities, you've got to be very careful that that's not biasing your management quantities. And that's where it comes into this last point here, is that if you're using that penalized likelihood approach and have the bias correction factor in there, then you have to make sure that the MSY calculations, any projections or other management quantities are based on average recruitment over a period where recruitment is estimated relatively precisely and is also considered to represent the desired conditions for your management calculations. Also, you should probably use dynamic reference points where this bias really is automatically taken care of. People have thought that coming up with the stock recruitment relationship is really the holy grail of stock assessment, because it's really difficult to find and really influential. However, I actually think that absolute abundance and natural mortality are actually the holy grails that we need to be looking for. So now I'll go a little bit into detail about the stock recruitment relationship. The first point is whether or not the stock recruitment relationships, the Ricker and the Bevan Holt, make sense. And one of the things is if you if you plot the survival that these relationships imply against eggs, you end up getting the survival decreasing fastest when the stock size is low, which is opposite to what you would think. You would think that the survival would actually reduce fastest when the stocks got closer to carrying capacity. But one way of thinking about it is that it's really just a model, and you just want to represent the shape of the stock recruitment relationship rather than really trying to base it on the theoretical understanding of that relationship. Because when you look at the Bevan and Holt and Ricker stock recruitment models, density dependence is unlikely to be linear. It's unlikely to be continuous at a constant rate. The density dependence probably occurs at some critical stage in that early life history. And the point I was making before is the strongest density dependence should be when you're getting close to carrying capacity. But despite all those issues with these models, the shapes appear to be somewhat reasonable. And so this is just getting into the point about the survival reducing as you get closer to carrying capacity. So the survival should look something like this. And if you go back to here, the survival looks more like that. So completely different than what you would expect. And that would produce a stock recruitment relationship that looks like this, where it's linear to start with because survival is constant. And then as you get closer to carrying capacity, that's when it bends over, but it also can often bend over more. And so we don't really see this type of relationship in most stock recruitment data we look at. One reason that this might be occurring is because the recruitment is actually being controlled by carrying capacity of the recruits. And those recruits will always produce enough adults that it doesn't fill the adult carrying capacity. So the adults are never being limited by their carrying capacity, it's just the recruits. And those adults will also always produce more recruits than the carrying capacity of the recruits. So you end up getting a constant number of recruits for a large range of adults. So you might end up getting this type of relationship, which is kind of what we see. It's like a hockey stick relationship that we often see in our stock recruitment data. And one way of thinking about that is it possibly could be the expansion of the adult population into unproductive habitat in terms of recruits. So even though the adults are there and there's a lot of them and they're spawning, it's actually not in a location where the recruits are successful. So the stock recruitment relationship is actually being controlled by the habitat for the recruits. But when you think about this, it makes sense for some species like moray eels that we see here at the top with little holes that they need to live in. But when you're talking about tuna that live in the pelagic environment, it's really hard to visualize what the limiting habitat would be for those individuals, particularly for the recruits or the young, the larvae and eggs and larvae. So is there a stock recruitment relationship? There have been a few studies out there, specifically this more recent one, and it tends to be mixed, where there's not really a lot of evidence or a lot of species that have clear evidence for a stock recruitment relationship. Most of it is either mixed or there's no relationship seen. Also, if you're trying to estimate the stock recruitment relationship inside the model, often you'll get estimates of bias, even though the assessment model is correctly specified. You end up getting a lot of estimates of really high steepness, or sometimes even some really low steepness values, which may not be realistic. So I think overall the conclusion is, particularly for estimation, assume steepness is one. Otherwise, you'll probably end up going mad trying to solve the problem. The next component I want to talk about is natural mortality. There's been a few, there was a special issue on natural mortality and several papers in that, and one specifically focusing on tuna. But in general, the conclusions are that natural mortality should be modeled as a function of length, using something like the Lorenzen relationship, particularly for the young individuals. The best way to estimate natural mortality for older individuals is, unless you've got real specific information on natural mortality, like tagging, good tagging data, which is often not available, is to base it on maximum age, and that should probably be used as a prior in the model, in the stock assessment model. For tunas in particular, the aging is really bad, and we don't have a lot of it. So rather than using age for the stock that you're looking at, it might actually be useful to use the age for any stock of that species. Should also consider sex-specific natural mortality. In tunas, we've been assuming that natural mortalities for females increases because the sex ratio tends towards males for larger fish. But now that we have a bit more aging data, we think that maybe some of that might be actually differences in growth between males and females. But that, again, that's something that needs further work. One of the problems with estimates of M from tagging data is the practicalities of tagging causes the tagging data to be probably biased, particularly for mixing, and specifically problematic for tunas. And so we have spatial temporal models which might actually provide us better estimates of natural mortality than the traditional models, or even cohort analysis that we've used for estimating M from tagging data. And for tunas particularly, until better information available, we might want to assume that M is the same for females and males, and model the difference in growth between the sexes instead of natural mortality. But again, that's a question that needs a lot more research. The next component is growth, and there's a few components here that I'll go into more detail in some future slides, but you want to make sure that you use a flexible growth curve so that where there's more information, or the ages where there's more information, doesn't control the growth of older or younger individuals where there's less information. You should be estimating growth inside the stock assessment model to avoid some of the biases of sampling by length. And when you do that, integrate the conditional age at length data into the model. Particularly for tunas, we have a lot of we don't have a lot of good aging data, and so we use length increment data from tagging to estimate growth. Unfortunately, you can't integrate that into most general stock assessment models like stock synthesis. So you have to somehow analyze that outside the model and then pass the estimates into the model. And you probably should be doing that by using it as a prior rather than fixed values. Also, a good suggestion is to always analyze the growth data outside the model and compare that to what you get from the integrated model, just to make sure everything's making sense. Because when you do it in estimate growth inside the stock assessment model, sometimes you might get weird things happening by the growth trying to explain model misspecification. You should always consider sex-specific growth. In most species, we're seeing some indications of that. And you should be modeling time-varying growth if there's adequate data. But that requires quite a lot of age data to inform those estimates. And there is a particular issue with estimating or dealing with spatial variation and growth, which I'll talk a bit more about in the next couple of slides here. So the growth information that we do have usually provides us good information about the growth or the length and age for the most abundant ages. And this is really useful if you're doing yield per recruit analysis or maybe an age structure production model. However, as soon as you start fitting the model to length frequency data, it can be the growth can be highly influential when you get the growth curve wrong for particularly the older individuals. So you really need to get a growth right. And this figure over here is just an illustration how the information about the maximum length can have a huge influence on some of the management quantities. And even the variation in length at age can influence the management quantities, but not to the same extent. This is just illustrating how a flexible functional form is really important. But just looking at the middle curve here compared to the two on the left and the right, which are more flexible, the von Bertalanffy can't bend over enough to fit those older sizes. And so you end up getting an L infinity that's much higher than the data suggests because the curve's too inflexible, and that will influence your management quantity. So you got to make sure that you use a flexible enough curve that it fits the data reasonably well. This one here is just illustrating how in the tuna assessments we fit to both otolith data, which typically this is daily otolith, so we can't age them for old individuals. So we rely on the growth increment data from tagging data here to estimate the L infinity parameter. And without that, we would have very little information or no information at L infinity, and it would be mainly coming from the assumed functional form of the growth curve. So because this tagging information is not available in stock synthesis, we can't use it. So that's why we have to analyze it outside and pull that information in. So I think a really good project for someone would be actually to develop the appropriate way to do this, particularly using, say, penalized likelihood, and writing up the code to put that into stock synthesis or into the next generation model that NIMS is working on. So now getting into a couple of more complicated issues with growth. The first one is temporal variation, which should be done if you have lots of information on growth, lots of age length data. And there's two ways that you can do it. One is the empirical approach, where you need to basically estimate the weighted age outside the model. But that might actually still require filling in gaps in the data. So there might be some complicated spatial temporal model that you might want to use to estimate the weighted age. Or you can do it inside the model. But again, now you've got to start thinking about how to model that time varying growth with functional forms and what parameters change, how they change. You should be using a growth increment approach to avoid changes in growth that are sort of unrealistic from one year to the next, or reduction in growth. But the main problem here is estimating the smoothness parameters for the time varying growth. And so again, in the penalized likelihood approach, that becomes problematic. And there's other things to deal with, such as density dependence growth and things like that. The one that actually is most problematic for tunas is spatial variation in length frequency data. And so if it's due to sampling, then you just want to make sure that you have a look at how that sampling is being impacted, and whether it's the time that samples were taken, or if the samples were measured in different ways, such as full length, total length versus fork length versus trunk length, and whether the conversion factors are correct or not. And that's something we've had to deal with in the tuna assessments. If it's due to age differences spatially, and then you probably want to have a spatial model So you can model that onto genetic movement, or you might be able to deal with it using sort of areas as fleets approach with age-specific selectivities. If it's due to differences in exploitation rates, then that definitely means that the spatial structure in the model, and you have to be trying to model that either as separate populations or some kind of spatially structured model. It is really problematic when it becomes that growth is varying spatially, because that means that you really should be using a spatially structured model. But often we don't have enough information to model the spatial structure and the exchange between the different areas. So you might actually be better off assessing each of the areas separately if there's really big differences in growth. Obviously, if there's big differences, it might indicate that there's less interaction between those areas. But really, it will require probably collecting a lot more data to deal with. It also might be due to selectivity, but if it's different gears, then you can expect different sizes from those different fisheries. But if it's the same fishery, why would they be getting different selectivity in different areas? And that's something that's needs to be considered fairly carefully before assuming that it's selectivity. With tunas, we see a lot of spatial variation in the length frequency distributions, and usually it's related to the maximum lengths that we see in different areas. And so that's indicating that there's some kind of difference in growth among areas, probably environmentally driven. And the problem that we have is we don't have a lot of information on growth, and so often it's coming from a limited area. So one approach might be to fit to the length frequency data in the core area where the growth information comes from, and then downweight or even eliminate length composition data from the other areas. But then the question comes, how do you expand the assessment out to those other areas? And so that's something that people are starting to think about and probably will be working on in the next year or two. Another important component of growth is that you have to model the variation of length at age. And typically it's kind of treated as a secondary issue, and probably rightly so, because it's less influential on the management quantities, but it actually can be quite complicated. And so there's a whole lot of different factors that can cause variation of length at age. The thing that we think of usually is that it's just the individual variation. And so some fish grow faster, some grow slower, but it also may be spatial variation. So fish from different areas have different growth rates. It might be temporal, that we haven't modeled the temporal variability, and so the variation length at age is taking up that. It could be variation in birth dates. So within the time period, like a year, if a fish is born at the start of the year versus the end of the year, the length at age for that individual is going to be differently if you particularly if you're using integer ages. There's also a variation in the date when the fish is caught as well, for length frequency data or for the aging data too. There's differences between sexes if that hasn't been accounted for, and also measurement error could be included, including some of that variability at length at age. And then once you've looked at all those different types of variation, it actually depends on the data you're using too and where it occurs. So like for otolith data, the temporal variation is not really that important in the daily otolith information, because you're measuring it if you're analyzing it on a daily basis and outside the model in the growth curve, or even inside the model if it's done correctly too. But if it's annual information or annual otolith rings, then you may not be taking that into consideration. Same thing for tagging growth increments, because you know the exact date that the individual is tagged and released. You know that information, and it can be used in the analysis. Whereas if you're looking at length comps and fitting to that, you know, those length comps are usually accumulating fish over the whole time period, over all areas, and so there's a different type of variation that can affect those. And so when you're fitting to sort of like daily otolith data and tag growth increment data in the model, you're not including the temporal variation in the variation on length at age, but when you're fitting to the length comps, you are. And so if you use the same standard deviation for variation of length at age for those different components, you end up getting a mismatch, and you might get problems in the fitting. Okay, so the next component is selectivity. And the first slide here is sort of the more standard stock synthesis type approach, where you using a separability assumption and the areas as fleet assumptions. And so each different gear type or sort of sub gear type should be treated as different fisheries because they have different selectivities. And when you're determining the areas as fleets, you should be analyzing the link frequency data using cluster analysis, because it's the link frequencies that you're trying to fit with these selectivities. And so that's how you should be defining your fleets. And one way of thinking about this is that if you've defined your fleets appropriately, then the selectivity should be similar to the contact selectivity, which tends to be fairly regular in shape. And so you'd expect something like a double normal distribution to represent that. And so any deviation in your selectivity estimates from a double normal shape, such as multiple modes, shoulders, long tails, suggest that you're grouping multiple fisheries together, and so they need to be split up. So you need to do some more work to determine those fisheries. So if that's sort of the assumption you're making, then the selectivity curves you should be using should be double normal type selectivity curves. In the past, we've used splines and sort of more flexible curves in our tuna fisheries, but I think that's the wrong way to go, because unless you're having time variation in those selectivities, you're actually going to have misfits as the amount of catch varies between the multiple fisheries that you're grouping into that single fishery and representing by the selectivity curve. Should always use the empirical selectivity diagnostic to see how well you're representing selectivity, although there might be too much emphasis on the largest size fish in that diagnostic. You should always consider using time varying selectivity for fisheries, because you would expect the selectivity change over time for fisheries due to the spatial nature of the areas as fleets approach. So that's one approach. The other approach is the SAM approach, which Anders uses in his assessments. And they essentially models time varying fishery selectivity, often by grouping multiple fisheries together and modeling that time varying selectivity, such as a random walk in age-specific fishing mortality. And because you have to estimate the smoothness parameter for that selectivity, you need to use a random effect state space modeling approach. There is some movement towards separating out the gears rather than combining them all together, and it seems to work okay. And this may partly be from the simulation analysis anyway that I recall, that most importantly for management purposes rather than for estimation. But I think there's one question that we really need to think about in this approach is how to deal with years with large time blocks of where there's no composition data. and how you combine the multiple fleets together in those particular situations. And so the composition data is actually not representing all of the catch, it's only representing part of the catch. So there is some work to do on selectivity, and unfortunately, I don't think we're going to have a manuscript in the special issue on selectivity. So that's something that needs some future work. The next component is getting more into the fitting rather than the underlying processes in the stock assessments. And the first one here is data weighting. And so this is basically to determine how much influence each data set and each data point has on the model, and also the estimates of total uncertainty coming out of the assessment. So there's multiple data types, but the two main ones are indices of abundance and composition data. And so for indices of abundance, there's been a lot of different ways of fixing the standard deviations for the likelihood functions. You can either estimate them, you can fix them constant for the whole time period, or they could be time specific. But I think the best way to do it is have time specific ones with an additive value to the standard deviation. And people have used smoothers fit to the indices of abundance to try and come up with that. But I think a more appropriate way is to actually have a structured smoother. And that would be by fitting an age-structured production model to the index with recruitment devs estimated. And that would give you a minimum estimate of what the CV should be. So it gives you a good idea of how consistent the index is with a population dynamics model. Also, it tends to overweight the index a bit more compared to some of the other data, which is something that's been suggested as well. But then for the composition data, it should really be based on the sampling design. And so this would produce estimates that are consistent with sampling error. And then you want to try and fix your model so that there's no model misspecification and you've modeled all the process or the main process variation. And once you've done that, if you compare the that input sample size to the effective sample size based on some kind of multinomial approach, that'll give you an idea of whether or not you've still got model misspecification or unmodeled process variation in your model. There's also might be some usefulness in comparing sort of the Dirichlet and McAllister and Iannelli approaches with, say, the Francis approach, which looks at the correlation and the residuals and seeing if there's any differences there. And if there are differences, that probably means that your model's misspecified, because a lot of the correlation and residuals is occurring because of the model misspecification. There's also some arbitrary stuff that you probably should be doing, is that if you really have some bad length composition data because the sampling design is poor or the sample sizes are really low or something, you want to really consider actually just removing that data from the model and sharing the selectivities or fixing the selectivities, particularly if the catch for those fleets is pretty low. Also, you want to consider removing some of the outliers. Like sometimes there might be some fish that are measured because they're undersized, but they were still kept or something like that, which tend to be quite different from the standard selectivity that you might expect. And so those will mess you up. So it might actually be better to remove those or possibly use robust likelihoods or something. So once you've got your models all run, then you want to combine them together. And so we had a whole workshop on model weighting. And the approach here is basically the approach I showed in that diagram of the processes that go into doing a stock assessment. So you start out with the conceptual model, develop a set of hypotheses about the population, and then use good practices to turn those hypotheses into stock assessment models. And then use diagnostics to fix and then finally reject or accept models. And so basically the whole point here is that you're actually only including reasonable models into your ensemble. So you don't have to worry too much about weighting them because they're all pretty good models. So the default approach is probably equal weighting. And that's because we haven't got a really good, reliable way of weighting the models yet, partly because our data weighting is not good, and also because our prediction type approaches are not predicting in quantities that we're using for management. However, if you really want to weight your models, hindcasting might be the way to go on a reliable index of abundance that's related to the management objectives. And that's something like spawning biomass, since we're using those in our reference point. You should always set the approach to the diagnostics and the model weighting in advance of doing any of this, of assessments or showing results, to avoid any subjective judgments which might be put into the model weighting. Also, you want to list the hypotheses that you didn't include because it was just not practical to include those in the ensemble, given the time and the expertise available. And also, you want to be realistic about the true uncertainty so that you include enough hypotheses to cover that uncertainty, because it's not only the hypotheses that pass through the diagnostics that are important, it's actually the hypotheses that you initially considered in your model that can influence the amount of uncertainty in the final management advice. Process variation is an important component that people are looking at now. The optimal approach is to use random effects or state space models, so you can estimate the variance of the process variation. However, a lot of our general models are still penalized likelihood approaches. So generally, we have to fix the variance at a reasonable value. One thing about modeling process variation, there's a lot of work, simulation analysis out there that says including process variation when it doesn't exist is okay. You don't get any bias, you just get a little bit more variance maybe. But that's not the case if you're modeling the process variation in the wrong process, because it will try and compensate for the unmodeled process variation and can actually greatly bias the results. And Nick Fisher's simulation work on this shows that clearly. So one of the sort of recommendations might be, if you're trying to model temporal variation and natural mortality, you probably should also be modeling temporal variation and fishery selectivity at the same time, to ensure that you're not biasing estimates because you're modeling variability in the wrong process. In terms of what to model variation in, we pretty much all model variation in recruitment these days. So that's something that's sort of should be done. Fishery selectivity, you probably should be, possibly in time blocks in some situations, depending on the amount of data. Process variation and growth. And when I say process variation, I'm typically meaning time varying changes in that process. In growth, probably only if you have the data to do it. And in most situations, we may not have that data. Natural mortality, it's really hard to tell if we should be doing it, because there's really not a lot of information about process variation in natural mortality in the data that we have. And movement, we have hard enough time estimating movement in a sort of a constant over time. So estimating time varying movement is probably something that's not going to happen very often, because we just don't have the data. Diagnostics, despite all the work that's being done and all the diagnostics have been developed and Felipe's simulation analysis, still a lot more research that needs to be done. I think here it would be great if there was a large project worked on this where we got every single peer-reviewed stock assessment, maybe in a consistent framework such as stock synthesis, and develop those as operating models for the simulation, and then tested a whole lot of different diagnostics and put it through some kind of machine learning approach to determine what results from diagnostics can tell us what's wrong and how to fix that problem. So a lot more research is needed here. Tagging, and so this is specific, not specific, this is particularly concerning for tunas, but I think is really important for probably most tagging projects. And because of the practicalities of tagging, tag mixing is a huge issue. So in general, because of the short-lived nature of tropical tunas as well, is that by the time they're mixed, they're probably dead anyway. So you're actually losing a lot of data if you try to deal with the mixing period by just removing the fish that are recovered rather than fitting to them. So it's not really advisable to integrate the tagging data into the stock assessment model, and really it should be modeled using some kind of fine-scale spatial temporal model that can deal with the non-mixing, but also make most use of all the information in the data. And this is something that Tobias and Anders are doing on our skipjack tuna tagging data. So we're hopeful that that's going to provide us some information on absolute abundance and natural mortality and things like that we can use in the assessment. But there's still a need for good estimates of tag reporting, tag loss, and tagging mortality to make these data useful. And we should be minimizing those in our tagging experience as well. But really it comes down to things like close-kin mark recapture are probably more useful in terms of tagging studies than traditional tagging. So that gets to one of my final slides, and I think I had this exact slide in the previous talk I did, and I haven't changed my mind yet. But really, a lot of the issues we have with fishery stock assessment can be solved or potentially solved by using close-kin mark recapture. And so the stock structure, which is the first component of the process of creating a stock assessment, close-kin mark recapture can tell us about the stock structure. It can provide estimates of natural mortality, which typically for most species and stocks we don't have any information on, and it's all based on relationships with things like maximum age, using data from stocks where the estimates of natural mortality are probably pretty poor. It also allows us to estimate absolute abundance, and this is really important because then we don't have to rely on fitting to the length composition data to estimate absolute abundance, which is highly problematic. So there's a lot of benefits. You don't have to worry about all the tag loss, tag mortality, except for and things like that. And also, we don't really need to know growth that well for the old individuals. We really need to know it mainly for the individuals that we're catching most of in the catch. And so a lot of real good benefits, and there's been quite a few close-kin mark recapture programs starting up, so we're going to get a lot more information on how well this works in the next 5 or so years, I hope. This here is basically a summary slide, I think, from my previous presentation, and I haven't really changed a lot of my opinions over the past few years, despite all the work that's been going into it. Although I haven't really reviewed all the presentations and manuscripts yet, so some of this might be changed, but there's a few things that are have changed a bit. Things like making sure that you consider sex-specific growth, don't use flexible selectivity curves if you're doing the fisheries areas of fisheries approach, but maybe if you're doing the Anders approach, you want to. Using the Lorenzen relationship to have age-specific natural mortality, use the maximum age proxy, possibly looking at using higher values of the recruitment standard deviation in the penalized likelihood approach. A lot more work needs to be done on diagnostics. So a few things there that are my sort of ideas about what should be done have been changing. Just wanted to put a plug in for the next CAPM workshop, which we haven't organized yet, but we've kind of decided on what we're going to do. So we're going to be doing a workshop on data poor and data moderate stock assessment methodology. We don't know where, we don't know when, but Dan Ovando, who just started at the start of this year at the Tuna Commission, is the one that's going to be sort of the lead on that workshop. So some of the people who've sponsored CAPM over the years, I probably missed a couple, but apologize for that. But some, either funding wise or logistic wise or both, want to thank the University of Washington School of Aquatic Sciences and Fishery Sciences, specifically with Andre taking a lead role in bringing in students, doing a lot of keynote speeches, and editing a lot of the special issues. So thanks, and specifically to the UW for their support to make CAPM successful. And so that's all I have this morning. And so looking forward to some good questions and some discussion.
Thank you so much, Mark. Sorry, I'm changing locations as roommates are up. Okay, so while folks are using the questions box in the GoToWebinar, as in filling in more, I have a starter comment that came in while you were presenting, Mark.
Mm-hmm.
And folks, if you'd also like to speak with Mark rather than type everything out, you should be able to use the raise hand feature. And this is how it works. We see you raise your hand. We have to give you permission to unmute, and then you, the user, have to then physically click unmute, and then you'll be able to chat with us. So while folks are getting ready, hi, Mark.
Hi, everyone.
The first thing, this is kind of like a share, but Trevor Branch, let me know if you want to talk more about it. During your stock recruitment section, and particularly that curve of survival and population size, and you said, we don't really see this in fisheries. Trevor wanted to let you know that he's currently working on a paper with some folks that they are seeing this relationship in whales between, yes, that's the plot there, in whales. And let's see, what else did he say? Where population growth rates are at maximum levels until the population reaches close to carrying capacity, and then growth slows quickly. Kanaji Yu, sounds like Alex Zerbini, Williams, and Trevor have a paper in review on this, so that's something to come on. Oh, here comes Trevor. All right, Trevor Branch. Looks like it's alphabetical by first name. All right, Trevor, let's see. Hey, unmute Trevor, and let's see if we can get you online.
Hey, Mark. Yeah, can you hear me okay?
Yeah, I can. Hi, Trevor.
Yeah, it's very interesting because, the very simple theta logistic model, you take a logistic would have survival declining linearly with carrying capacity, or growth rate, really. But if you put that little theta parameter on it, you get a curve that looks just like this with a high value of theta, or Z as we call it in the IWC baleen wells. And what we did, we looked at 4 baleen well populations with lots of data from low abundance to high, because it's very hard to estimate that parameter. And you do seem to see this kind of pattern show up for baleen wells. I don't know if it's true for fisheries though, but it would be interesting to check that out.
Yeah, I mean the thing that we thought about this for was for sharks, and so that's a species where you might expect something like this to occur, particularly with the low fecundity shark species that only have a few pups.
Yeah, that makes sense.
Thank you,
Good talk,
Trevor.
thank you.
Sorry, I interrupted you. Was there something else, Trevor?
Just for saying good talk.
Thanks.
Next up, I'm just doing this in the order that I received them. We have Nick Fish. No mention of Bayesian methods. Do you not see that as a viable approach to assessment estimation and estimation of process variances as it can currently be implemented in SS or stock synthesis?
Yeah, so I personally, I don't differentiate between Bayesian likelihood approaches that much, in the sense that we often put priors on the penalized likelihood approach, and then if you start doing the integration using random effects, using TMB or something like that, you're integrating across those process variation. But yeah, he's right. I mean, when you start doing a Bayesian analysis, you can automatically integrate across the process variation. And if people remember back in the old days when Andre and Murdoch McAllister, Tim Hammond and those guys were doing Bayesian, yeah, they were estimating recruitment variation in their age-structured models, and I'm guessing they were probably estimating the standard deviation for the recruitment variation in those models. The issue is that you have to get good convergence in your models, and a lot of the complicated models we do for in-stock synthesis, people have had issues, particularly in the past, with convergence and that. And so I haven't done Bayesian a lot since I started doing hardcore integrated analysis, because basically all your priors became uninformative, and then you had to think carefully about what the priors were, and if you got it wrong, you could influence the results. And so I kind of stuck with the likelihood approach. But yeah, Nick is right. If you go full Bayesian, then you can deal with a lot of those process variation and estimating the variance parameters. Whether or not you can actually estimate them and get a converging model if you have multiple time varying parameters is another question. But yeah, good point.
Thank you. I have two follow-up comments that I think are saying the same thing. One is from Cole Monahan saying, there's a manuscript that Cole and probably co-authors are working on that are in review for this special issue related to Bayesian assessments. So Nick, there'll be a little something for everyone, including you Bayesians, in the special issue. And then Andre said, got nuts, which I'm assuming means no U-turn sampler, which is probably related directly to Cole's paper.
Yeah. Well, that's good to hear. I'm glad Cole put together a paper for the special issue. That's good.
Yes, and Andre, I see you have a verbal comment. Don't worry, your time to shine will come right after Ian Stewart's comment, or question rather. Thanks for a great talk, Mark. We have come a long way in the last 10 plus years, and it is good to see some convergence in common practices. You recommended fishery data be modeled as a removal fleet with catch-weighted composition data, and an index fleet with spatially weighted CPUE. In that approach, where does the information come from for selectivity for the index fleet? Are you suggesting estimating the index selectivity without any composition data?
So the index composition data comes from the same composition data as the fishery extraction, except for it's spatially weighted by the CPUE, whereas the fishery extraction composition data is spatially weighted by the catch. And so the index is representing the population size structure or age structure, and the catch is representing the catch age structure. So those are treated differently, and then they have different selectivity curves, and so you estimate them separately. You might be double using the composition data, but because you're weighting one by catch and one by CPUE, I don't think it's really a big deal.
Thank you. All right, so in my queue, I have Andre, and then I also see Chinta, and I also see Kelly Johnson. So I'll go in this order. first, let's start with Andre's. He wrote Q1, which implies that there's more than one. First question for Andre, and Andre, I'll give you unmute permission in just a moment. What is the factor do you think, sorry, let me start that over. What is the factor you think, if get wrong, has the largest impact of estimation of biomass, M, and reference points?
Yeah, interesting. I think it could, as asymptotic versus dome-shaped selectivity. So assuming asymptotic selectivity when it's really dome-shaped and you're fitting to composition data is probably really big. L-infinity for the growth curve when you're fitting to length composition data is really big. I think those two are probably the biggest. But if you're not fitting to length composition data, I think natural mortality is probably the biggest issue.
Andre, you're now unmuted. Feel free to respond to Mark on this point or go ahead and launch into your steepness resistance.
Yeah, I will avoid discussing steepness. My lawyers have told me it is not in my best interest to comment on steepness. But yeah, I think, so the question, which was poorly written clearly, is we've been really good about coming up with thousands and thousands of suggestions. And I think from a practitioner's point of view, having a ordered list of these are the things you should be really caring about, as opposed to worrying about the angels on pinheads, which I suspect some of the things that we're talking about tend to have little consequence, but we feel good about them. And there, I agree certainly with the cryptic biomass thing. I would say spatial structure is related to that. So I think as we move forward, trying to identify, what are the things we really should be focusing on, because we don't want to give people advice of here's a list of 1,000 things, and then they don't do the right, they don't focus on the right ones. So I have a horde of questions, but I'll restrict myself because that's what I'm going to do. You referred to close-kin mark recapture. Just for those who are interested, we being CSIRO and my lab, have integrated close-kin likelihood into stock synthesis, at least for a fairly simple case. So if you've got close-kin mark recapture data, we're hoping to submit the paper in a couple of months, but it can be done. It turns out that little figure that you showed that Mark puts up is a little simple for most of what we have to do. And in the work I've just completed, I've actually, Robin Thompson, we ended up having to put in grandparent-grandchild likelihood probabilities as well as POPs and half SIBs. So as we get into this in a bigger and better way, there's a lot more going on than I think we initially thought, that all you need is parent-offspring pairs and your life is good. I think there's a lot more to it. But as I say, I think that Mark Bravington and those guys did integrate close-kin into sort of integrated assessments, but bringing it into synthesis will hopefully increase the discussion. So I'll stop there.
All right. Mark, do you have any follow-up from Andre, or do you feel pretty good?
No, I just think the more people that start doing this, the more we're going to learn. So I think it's great.
Next, what I've done, Chinta Pereira, let me know if I can pronounce your name better. I've allowed you to unmute, and I see you are unmuted. Go ahead and come on in and ask your question.
Yeah, first of all, thank you very much for your nice presentation, informative presentation on stock assessment. Can you hear me?
It's a little muffled.
I am Chinta from Sri Lanka. You have mentioned not to use tagging data in stock assessment model. Could you please kindly explain it?
Yeah, sorry, I couldn't quite understand the question.
Hello?
Chinta, were you asking about incorporating tagging data into the stock assessment model?
Yeah, really.
Okay. So the growth increment data or the mark recapture data?
Yeah, recapture data.
Okay. Yeah, the problem is that the often we can't tag fish in proportion to their abundance, or they don't mix very quickly, and so we end up getting non-mixing of the tags with the untagged individuals. And so in our stock assessment models, we usually use large boxes where we have movement from one box to the other box. But because you don't have that mixing in there, you'll end up getting biased results because the tag fish are moving at a different sort of, or they basically, yeah, I guess moving and in a different abundance to the untagged fish where the fisheries are operating. But to overcome that, if you use a fine scale spatial temporal model, then the fish only have to mix within a little temporal and spatial scale, and so that usually is not going to have a big influence on the results. The problem with the fine scale spatial temporal models is they're very computationally intensive, so you can't really model that inside a normal stock assessment model, although I know a few people have done some fine scale spatial temporal stock assessment models. But Anders and Tobias have come up with a very efficient way of analyzing that data and using fine scale spatial temporal models. And hopefully that will provide us with estimates of things like natural mortality, fishing mortality, and absolute abundance that we can then take and put them into the full stock assessment model.
Thank you so much, and again, thank you so much for giving an opportunity to join such important webinar today. Thank you.
Thanks.
Thanks for joining us today. Mark, I'm going to scroll down to Kelly Johnson. Kelly, I know that you typed it in chat, but come on in. Ask us your question. Let's see. You will have to, there you go. Come on in.
I'm sorry, this is Christine. I think I must have clicked Kelly's join link.
Oh, hi, Kristen.
Christine Davis. Are there two Kellys? Sometimes that happens in this.
Yes, there are. I didn't notice until just now.
Sorry, Kelly, that I'm impersonating you. I will ask my question. So you talked about the need to model error in the correct process when you're talking about state space modeling. And so I think that felt kind of ambitious to me in terms of knowing what the correct process is. So can you talk about how you would explore the data to identify which of these processes you think is the most important in that context?
Yeah, so it is pretty tough to work out which process is the right process, and I'm not sure if there's been enough simulation work to comment too much on that. But maybe Nick, because Nick Fish is on the call, so maybe he could come in and provide some comments on that as well. But I think the point might be to make sure that at least you are modeling enough processes that you cover the right process. And so that's why I suggested that if you're modeling time varying natural mortality, which is a lot of people want to do, that you probably shouldn't be doing that if you're fixing fishery selectivity, because fishery selectivity might be more likely to change over time. And you probably don't want your natural mortality trying to compensate for unmodeled time variation in fishery selectivity. And so on the slide here, I assume you guys can see it, that hopefully, I mean, this is sort of the priority in terms of modeling time varying processes. So I think you should be modeling recruitment, which everyone does anyway. And then selectivity is the next one. And then growth if you have the data. If you don't have the data, I'm not quite sure what would happen. And then natural mortality would be only after you've been modeling recruitment and fishery selectivity and possibly growth. So that's kind of my thoughts, but I really haven't done any work on this, so I don't know if these are right or not. They're just sort of intuitive.
Thank you. Sorry, the real Kelly Johnson. Let me know if you do have an additional a question to add to the queue. Andre, is your hand up related to the current topic, or is this a switch in topic? You gotta unmute. Nope, hand down. All right. I'm moving on to the next written question. Thank you, Mark. The next question here is from Josh Sanner. Do you have strong thoughts on whether the sum to zero constraint that frequently gets applied to recruitment deviations is a good assumption to make, or what under what conditions should it be used?
Yeah, good question. It's used a lot. I actually don't think it should be used. Just theoretically, it kind of doesn't make sense to use it. It also might mess up likelihood profiles. It also might cause an estimate of recruitment in a period where there's little data to be estimated at an extreme value, like your most recent recruitment. And this also comes into play when you're thinking about how to fix your standard deviation for the recruitment deviates. Some people are suggesting that maybe you should use, or they actually have used, higher values of that to allow the recruitment not to be penalized too much. And so in those particular cases, it would probably even be a worse of an issue in terms of summing to zero. So I would suggest not using it. That would probably be my opinion, but again, I haven't done a lot of work on this to determine the benefits of doing it versus the benefits of not doing it.
Thank you. Andre says he agrees with you on the sum to zero topic. I have a question from Momoko, and then Brian Langseth, I'll get to you. And Andre will probably not agree on this next one, Mark, but that's part of the fun of the workshop. So Momoko is asking, or saying, thank you for this great seminar. If we assume H is equal to 1, how do we select the target and limit reference points? Do you have any good practice recommendations there?
Yeah, I don't really have any good practices, but I can tell you what we've done. So for our limit reference point, we choose a value where the recruitment is reduced to 50% of the unexploited recruitment when steepness is 0.75. And so we're assuming that 0.75 is a conservative value of steepness for tropical tunas. And that seems all reasonable, and people like it until you tell them what level that is, which is, I think it's 7.8%, and then they go ballistic and say it's too low. So that's one thing. For the target reference point, which we just put together for skipjack tuna proxy, I can't remember exactly what it is, but I think it's something, I could get this wrong actually. It's something like what the spawning biomass level is when you assume steepness is 0.75 or 0.3, whichever is the highest. And the reason for doing the 0.3 part of that is based on our estimates for big eye and yellowfin, and the fact that because we often are catching really small fish, that kind of messes up your reference points a bit, because the reference points are somewhat sensitive to the selectivity that you're using to calculate them. And so we don't really want to be having a reference point that's defined a lot based on catching small fish. And so I think that's why we chose the 0.3 as well as part of the proxy definition.
Thank you. Andre, go on. Andre has a verbal comment, so come on in.
I've got a couple. Firstly, just back to the sum to zero thing. There are definitely good reasons not to do it. One that I hadn't thought of that occurred to me happened to me recently was I had an assessment that I updated, and a recruitment essentially is a steepness equals 1. So for once, I'm agreeing with Mark. And if you add a very strong recruitment, right, and you're estimating them all well, that actually affects R0. Because basically you've gained more positives, so you have to end up with a 0 average, so you end up increasing the mean, and so you can end up with some very funky things with sum to zeros. Also, it does some nasty things to MCMC as well. So that was just one point. But just going back to the steepness thing, Mark, because you had to go there. I mean, the other thing that I think is worth bearing in mind on this discussion is tuna assessments, and dare I say, groundfish in the North Pacific and places like that, tend to only assess the period of time for which we've got good data, or more or less good data. Some of the tuna assessments, that's dubious when you go back to 1950. But when you've got stocks like rockfishes, where we tend to go back a long way, assuming steepness, essentially assuming constant recruitment for estimation purposes over the entire period starts to get questionable. So I think the discussion is also related to how long the assessment period is and how much you're using the stock-crude relationship, whether it's flat or not, to extrapolate into places where you have no data. Whether you should do that is another question, but just pointing out that I think the steepness discussion, in your case, you're estimating within the range of the data, and you generally got somewhat decent estimates of year class strength. Once you go outside of that, I think the discussion gets more subtle.
Yeah, and also it depends on how low the population's been exploited too. If you haven't gone below 20%, it probably doesn't matter.
I want to hop in here. I think this is related. Cole said bounded dev vectors were an experimental feature of ADMB and does not work with MCMC. So I'm not sure if that also helps with Andre's recent woes.
Yeah. I mean, Andre also brought up an interesting point about the initial conditions, which is not something that I've presented here or hasn't really been a big thing at the CAPM workshops as well, but is actually quite important is when you start your model and how you start your model. Is it an equilibrium? Is it you're estimating the numbers at age? And do you start at the start of the catch history, or do you start when data becomes reliable?
Thank you. Thank you everyone for your patience, as it's a little bit easier to do in person, but I'm trying to weave these together as thematically close as possible. The next person in the queue is Brian Langseth. Brian, it should allow you to unmute yourself. Come on in with your question and comment.
Sure, thanks. Hi, Mark. Question,
Hi.
the March workshop was specifically tuna best practices, which obviously makes sense with your agency and expertise. I imagine much of what you've shared today applies across all species, but are there any specific instances where kind of your presentation applies more to tuna than to other species?
Yeah, so things like the stock recruitment relationship, because they're highly fecund pelagic spawners and spawn all year round and stuff like that, the tropical tunas anyway, might be quite different from something like a shark, right? Also maybe groundfish and things like that, which have sporadic recruitment. So that there are some differences in terms of life histories. Again, things like using maximum age, for a tunas, maybe it's quite good if you could age them well, because they only live to a few years, and if the aging era is not that bad, it doesn't matter. But maybe for fish that live to 100 years, if the aging era is out by 10%, that could maybe make a big difference in natural mortality estimates. depending on, what you got. Yeah, so I think in general, I think the general concepts are probably okay, but when you start looking at the specifics, how to implement a general concept, it might differ among species and stocks.
Thank you. And I think Andre is adding to this discussion the focus on length data. Most groundfish has some length age data.
Yeah, yeah. The lack of aging is pretty bad for tunas. Even with the tunas, there's some differences too. Like the tropical tunas, because of their lower value and how difficult it is to catch them, exploitation rates tend to be not so bad. But things like bluefin tuna, which are highly valuable and maybe easier to catch, they've been depleted to really low levels, like to 3% of their virgin. So the processes that go on when you're that low might be quite different. One of the reasons why we don't think so much about the stock recruitment relationship is if your population's gone to 3% and then gets up to 20%, but the recruitment doesn't change much, then there doesn't seem to be much evidence of a stock recruitment relationship.
Thank you. All right, I'm catching up on the queue. Rick thought this was 10 minutes ago now, so I apologize for the lag time. But Rick also throws in this comment. He recommends you should do time varying natural mortality for forage fish, as predation is likely quite variable. Rick, let me see if you want to speak more on that, or Mark, if you have a follow-up question for Rick regarding that.
Not really. I mean, if the species is at an adult size that's pretty small and they're a forage fish, then yeah, temporal variation and natural mortality might be very important. I guess the question is where you get the information from, and if you don't have information in the data, what happens when you try to estimate time varying natural mortality? If you have an estimate of or a good assumption of the variation, is that good enough? Or do you have to actually have information that estimates the specific value for each year to avoid any biases in the estimation process?
Awesome. I found a question.
This Rick, I would just follow up there on that one, Mark. This is Rick. I just add that, we do now have in synthesis a predation option. So if you have a time series of predators, you certainly could use that as essentially a covariate for that time varying M.
Mm-hmm.
Thanks, Rick. I must apologize to Steve Cadron. I completely missed your closed-kin question, so it's coming up now. All right, Mark. Closed-kin marker capture can estimate adult biomass and survival, but how would we derive reference points for status determination or optimum yield?
Well, okay. If you have estimates of growth for the main sized fish, hopefully you have natural mortality from closed kin, you have absolute abundance, and you have some assumption about the stock recruitment relationship, so you can estimate your reference points. The question is, I guess, what you do with the juveniles in terms of their natural mortality, and their abundance, and then hopefully you would get some information from some of the composition data, or maybe you would have a traditional tagging analysis of juveniles that you did to get estimates of abundance for them. So yeah, so despite the fact that close kin can solve a lot of these problems, as I think Steve was pointing out, it's for the adults, not for the juveniles. So you still have to somehow come up with estimates of those values for the juveniles if they're an important component of the management advice.
Thank you. I have another closed-kin question here from Nikolai Klebansky. Is there a set of good practices for fishery-independent surveys for prioritizing species and collecting genetic samples for doing closed-kin marker capture for a whole regional portfolio of stocks?
Probably not, but I wouldn't be the person to ask. But close-can mark recapture would be a good topic for a CAPM workshop, maybe in a year or so when there's a few more applications that people have applied, so that there's a bit more knowledge out there that to present and discuss.
Thank you. We have a comment from Andre. Integrate CKMR into the assessment, 3 exclamation points. I think you two are in agreement on this topic. This is my last question I have in the queue so far, and it's from Katarina War. I'm curious about the steepness equals 1, practice and simulations / projections. Wouldn't it produce very optimistic and maybe unrealistic projections at lower spawning biomass? Would you use the same type of assumption when using an assessment as an operating model in a closed loop simulation?
Yeah, obviously for estimation, it's not such a big deal, except for when you're going back to the start of the catch history, like Andre was mentioning. But yeah, any kind of management kind of calculation, it becomes a problem, including projections. And actually, if I remember correctly, and I might get it wrong, but actually assuming a strong stock recruitment relationship is actually worse for rebuilding plans, because as the population rebuilds, the recruitment should increase, so the population will rebuild a lot faster. And I think there's been several situations where the population hasn't rebuilt as fast as the projections suggest, because the stock recruitment relationship, or the steepness of the stock recruitment relationship, was over assumed or something.
Thank you. So my queue is now empty. I see some lingering hands up from maybe Rick Mathot and Andre, but those could be remaining from before. Okay, oh wait. Okay, Rick, come on in.
Here we go. I'm in.
You're in.
Mark, in response to what you just said about steepness and rebuilding plans, the converse of that is that if you do not assert some degree of ability of the mean recruitment to decline, you could be biasing your model result against detecting a decline in recruitment near the end of the time series. So it cuts both ways. If the Ds are penalized from a mean, they're penalized away from seeing a trend. The way I've dealt with this is to not use zero sum, and I agree with that completely. We should not be using the sum to zero constraint on recruitments. But I've also seen that if you try to use a reasonable sigma R, then you need to downweight the penalty on the recruitment deviation, so they essentially can be more free to deviate from the relationship. So if you use deviations from a mean, you need to not use a full penalty on those Ds, otherwise you're penalizing things towards only seeing a mean. But so I think the important thing is that we perhaps should be not thinking of it as a true spotter recruit curve, and perhaps simply as allowing the model to estimate a 2-parameter relationship, to simply a trend in recruitment or a dog leg in recruitment over time, so that it has some ability to detect a downtrend.
Andre, did you want to come in and join the conversation? You said something about more subtle than that.
Yeah, good. This is for anyone who's a UW student. This is the kind of question I like asking for general exams, just so you know. But yeah, Mark, you got first part of it right. But remember, if you assume steepness equals 1, essentially you're assuming that you won't get higher recruitment in the future, which affects your target reference point as well. So there are competing effects going on. If you say steepness equals 1, why are you even wanting to recover anyway? Because what's the point? But your mean recruitment determines your target reference point, which is related to your rebuilding target. So higher steepness, all things being equal, will tend to have a higher rebuilding target, which so there's more going on here than just that first order effect that you raised.
Mm-hmm.
Thank you. Mark, we've got about 15 minutes left. And so you've been doing a wonderful job in the hot seat, the discussion seat. Is there anything that you'd like to hear from our audience? I mean, is it also fair to say, hey, everyone, if you've been sitting on a data limited project that you've been wanting to start, now's a great time because 2024, Dan Ovando is going to be organizing the next CAPM workshop. But anything in addition to that you'd like to hear from the wonderful group of fisheries scientists that you've gathered at our workshop today?
Yeah, not that I can think of off the top of my head, but yeah, I just want to reiterate that the special issue still has a month left. If you have something you want to submit to it, it's a good place to publish because of the focus people put on those special issues. And yeah, for the data poor assessment, if anyone's got a location or funding, that would be interesting to us. Yeah, I just want to encourage people to be involved and share their research, and CAPM is a good place to do that because we get a lot of people coming to the workshops either in person or virtually. Yeah.
Thank you. If you have the time, I do have another question that came in from Alan Hicks. Is that okay?
Sure. Yeah.
Yeah, Alan wants to know, what does R0 mean if you do not allow devs to sum to 0? So this might bring Andre and Rick back too. Doesn't this mean that average recruitment is R0 times the mean of the estimated deviates for that period in which they are being estimated?
Yeah, so I'm not exactly sure about the sum to 0 issue in terms of that, but in general, you want to make sure that whatever you're using in your management quantities is equal to the average recruitment over the period you think is representative of what you want to produce, and also that the estimates for those particular years that you're doing it is estimated precisely. Because there's a lot of things, if you get the standard deviation wrong, the bias correction factor, you haven't done the ramp or something like that, you can actually get an R0 that's quite different from average recruitment over a period that's reasonable. So I think I don't know if I thought I put it in here, but if I didn't, one good practice is to double check that your average recruitment over a period that you think is reasonable is similar or not, if not the same as the R0 that you're using in your management quantities.
Andre or Rick, did you want to add to this?
Yeah, I think my hand is up. Yeah, so Mark, you're probably closer to this than I am, but New Zealand has that explicitly built into the Castle formulation. So just to sort of reiterate that, firstly, the sum to 0 constraint is on the devs, which is in log space, not in normal space. Whereas if I remember correctly, and I probably don't, the New Zealand has a sum to 0, average recruitment constraint in arithmetic space, which is what you're really referring to. And the other thing about sum to zeros is, don't forget you've still got a sigma R penalty, Alan. So the sigma R penalty has a similar property to the sum to 0 constraint, because if you think about it, the derivative of that penalty with respect to your parameters has to equal 0. So it sort of does something quite similar, to be honest, but it doesn't have the nastiness that Cole pointed out about how it messes up things like MCMC convergence and stuff. So just having a normal sigma R penalty tends to stabilize things a little bit as well.
Alan, I see your hand up. Come on in, unmute.
Great. Can you hear me?
Yeah.
Perfect. Yeah, that's great, Andre and Mark, and thanks so much for that. I've seen some assessments where they estimate a small period of time of recruitment deviations, and they're really influenced by a couple big ones or a couple small ones. And so the actual mean of those deviations is different than zero. And so you have a R0 in a period without estimating recruitment deviations, and then a very different average recruitment over a period where they were estimated. But yeah, I agree with what you're all saying. If you have good, precise estimates over a long period of time, then they should sum to zero just based on that penalty. Something to be aware of, so thanks.
Awesome. Okay.
Yeah, I just want to add to that and this is just to re-emphasize it, is that if you get the bias correction factors wrong, it goes directly into the estimate R0, and you know, you can change things like the fixed value of the standard deviation for recruitment, and then that can change your management advice just because, you know, of the bias correction factor. So it's something that's really important to keep an eye on.
All right. I think this has been a wildly exciting, well, for stock assessment scientists workshop. So thank you. One thing I wanted to confirm for folks, because some folks were asking, this is being recorded. It is a series of holidays this week here in the US, so it's going to take a couple of days for my lab mate, Mikko Keenan and Mark Maunder, to work through where they will upload the video. I imagine maybe the CAPM YouTube, like Mark's other two think tanks, it'd be nice to keep like with like, but we'll let Mark and Mikko work that out offline. So again, thank you so much, Mark, for coming and sharing these summaries from hours and hours of hard work from across our field, from experts from across our field. And we are looking forward to what you all get up to next with the next Kaplan workshop, and of course, reading that special issue of Fisheries Research in a couple of months' time. Mark, thank you so much for joining us today.
Yeah, thanks a lot for having me.
Yeah. All right, we'll see you all in a couple weeks for the next think tank. I believe it's Daniel Villa. And with that, everyone have a wonderful day and a nice holiday week here in the US.